Hello everyone, in this video we are going to start study about an interesting data structure known as trees. Till now you might have heard about data structures like arrays, linked lists, stacks and so on. These data structures are linear data structures. For example, take a linked list. In linked list you have a set of nodes where each node points to the very next node. In this linked list, suppose there are three nodes. Let us say this node stores the data 4, this stores 1, this stores 8, and this is an end pointer. What is the start of this linked list? Correct. This node points to the start of the linked list. As you see that in a linked list, there is a logical start, there is a logical end pointer, and also there is a logical meaning of the next element. These are the properties of linear data structures. What is a data structure basically? Data structure is nothing but a way to store and organize data. In a computer system. How will you choose which data structure is perfect for a particular problem? You might choose this based upon some different kinds of criteria. The first criteria might be the type of data that you are representing. The other decision might be to reduce cost or time complexity for frequent operations. Example, suppose you are given a problem that hey, we are given a set of numbers and multiple queries where you have to find if a particular number exists in the array or not. What data structure you will use? You can use an sorted array and apply binary search. Or you might also use a hash map. Sometimes the choice of data structure is based upon reducing space complexity. Tree is a data structure that is most suited for hierarchical type of data. Consider the organizational hierarchy of a big corporation. There is a CEO. Under the CEO, there might be multiple presidents. Similarly, under each president, there might be multiple vice presidents. And so on. This is a type of data that is one of the most common types of data that can be represented using a tree. Why is it even called a tree, by the way? There is a very similarity between this data and an inverted tree. What are these things in the tree? Yes, these are the leaves. Similarly, in our tree data structure, the end nodes, had there been no other nodes downside it, are known as leaves. What is this in the tree? This is a root. Similarly, the top of the tree data structure is also known as the root of the tree. So basically, a tree data structure represents a inverted tree. Now, let us look at some terminology related to trees. Let me draw a formal tree for an example. And let me number the nodes in some way. 1, 2, 3, 4, 5, 6, 7, 8, 9. Great. The very first terminology that is related to tree is the root of the tree. The root of the tree is nothing but the node which is at the very top of the tree, or the node under which all the other nodes of the tree lie. So in this example, 1 is the root of the tree. Now let us discuss the parent-child relationship. As there is an edge from 7 to 9, 7 is known as the parent of 9. Similarly, 9 is a child of 7. Now, what is the case of 6 and 7? As 6 and 7 have the same parent tree, 6 and 7 are known as siblings. Okay. Now, the very common term that you will see when reading about tree algorithms is a leaf. A leaf is a node that has no child. So, in this example, node 8, node 5, node 6 and node 9 are leaves of the tree because they have no child of themselves. Now consider a path from the root of the tree, that is 1, to a particular node, for example 8. We see that on this path the nodes that lie are 1, 2, 4 and 8. If a node lies on the path from root to a particular node, for example 2 lies on the path from 1 to 8, 2 is an ancestor of 8. Conversely, 8 is descendant of 2. Now we studied about ancestor and descendant. Now let us see for a particular node 8 again. What is the length of the path from 1, that is root, to 8? As we do here, the length of the path from 1 to 8 is 3. The length of the path from root to a particular node is known as depth of a node. In this case, the depth of node 8 is 3. Similarly, what is the depth of node 3? As the length of path from 1, that is root, to 3 is only 1, which means depth of 3 is 1. Similar to depth, there is another term which is height. People tend to confuse between depth and height. As depth is the length of the path from root to a node, height is the length of path from node to farthest leaf in the subtree rooted at node. Let us take the example of node 3. In node 3, what is the subtree rooted at node 3? Correct. This is the subtree that is rooted at node 3. What is the farthest leaf from 3? As you can see that the farthest leaf from 3 is the node 9. So, what is the length of the path from 3 to 9? It is 3, 7, 9. So, the length of path is 2, which means height of node 3 is 2. So make sure you understand the difference between height and depth clearly and don't confuse between those. This was the definition of height of a particular node. Now, what is the height of the tree? Height of the tree is nothing but the height of root node. So, in the example above, what is the height of the root node? Clearly, the longest leaf from the root 1 is 8 or 9. What is the length of the path from 1 to 8? As we saw earlier, it is 3. Thus, the height of tree in the above example is 3. Great. So we have till now discussed some of the terminologies related to trees. Let us discuss a few properties of the trees as well. The very first property of a tree is that a tree with n nodes has n minus 1 edges. Why do you think that is the case? Let us go back to the tree that we draw above. We see that for all the nodes other than the root node, there is an edge pointing to the node. For example, for the case of node 2, there is one edge that is pointing to the 2. Similarly, for node 4, also there is only one edge pointing to the node 4. Similarly, for node 5 and all other nodes. So we see that there is one edge from to any node other than the root. So for n nodes, all nodes other than root have an edge pointing to them. This means there are n minus 1 edges. Based upon the properties of the trees, different types of trees are also defined. So, for example, if all the nodes of a tree have less than or equal to 2 children, this means the tree is a binary tree. Extending this thing, if all the nodes of the tree have less than or equal to n children, implies that the tree is an n-ary tree. Let us take an example. Do you think this particular tree is a binary tree? No, this tree is not a binary tree because we see one node has 3 children. Implies that not binary. Do you think this is a ternary tree? Ternary is also known as 3-ary. We see that this node has 3 children, this node has 1, and all other nodes have 0 child. As we see that all the nodes in the tree have less than or equal to 3 children, this means that this is a ternary tree. Similarly, there are many other properties of the trees of different kinds of trees. For example, there is a binary search tree. We will discuss this in depth in a future video, but as an overview, a binary search tree has a property that all nodes in left subtree of a node, have values less than the node value, and all nodes in right subtree have values greater than the node value. Now let us move to some of the applications of this tree data structure. A tree data structure is a very important data structure and is used in many real-life applications. As we discussed earlier, the tree data structure is the by default data structure for hierarchical type of data. So, it is used in applications that resemble hierarchical data. Example, the file system of your computer. How is a file system like? There is a parent directory, or which is also known as the root directory. Inside this root directory, you might have multiple other directories and files. For example, this is a directory D1, D2. This might be a file F1. Similarly, there might be another directory D3. Each of those directories can in turn have other directories under them or files. For example, suppose D1 has one more directory inside it and two files. A file cannot have anything inside it, so file in a file system will be a leaf node. There might be a directory, for example in this case D2, that might not have anything inside it, which can be an empty directory. I hope it is clear as to why tree data structure is one of the best data structures to represent your file system. The second application of tree data structure is by different types of trees that exist. For example, there is a tree known as trie. Trie is a data structure that is very good to represent dictionary. It allows us to search if a word of length m exists in the dictionary in order of m time. We will study trie in depth in one of our future videos. Similarly, as I talked briefly before, there is a type of tree known as binary search tree. Binary search tree allows us to find if a data exists in the node, exists in the tree in order of height of the tree. That is why you will see that height of the tree is very important factor in analyzing the complexity of tree algorithms, and we will study it in depth also in future videos. One last application of tree that is commonly used is in routing protocols and internet. Are you guys aware of a DNS? A DNS is represented like a tree. Suppose you have to find the address of www.google.com. A DNS server is organized like a tree. There is a root domain dot inside under which there is a .com, under which there will be a .google, under which there will be www. Similarly, suppose it had to represent facebook.com as well. To represent facebook.com, the root domain will remain the same. .com will also remain the same, but there will be another Facebook here. Great. I hope it is clear as to how a DNS server might now be resolving your queries. That is all that is for today's video. In the next video, we might be seeing other important characteristics of trees and we'll be studying different types of trees in depth. So make sure to subscribe to the channel and look forward to our future videos. Thank you.